Hello friends, in today's video we learn about homoscedasticity or equal variance of the EY term. Okay, so this assumption is one of the assumption about the classical linear regression model. Okay, so it means that the conditional variances of UI are identical. Okay, so when we are dealing with that given the value of x, the variance of UI is same for all observations. This is the conditional variances of UI. Now we denote these conditional variances like this. That is UI given the value of xi. Okay. So for each xi, value, the error term around that value must be equal for all the x observations. Okay, so we are denoting that expected value of ui minus the expected value of ui given with the value of xi, that means the mean here whole square is equal to the sigma square. Okay, so it is telling y populations corresponding to various x values have the same variance, number one. Then the variance of ui for each xi, that is the conditional variance of ui, is same some positive constant number equal to sigma square. Okay. Now the we know about the formulas like this, right? We know about the formulas like this. So we have already done this part, which is for x. If it is x variable, then we find the variance like this. And we studied about the sigma square estimate. Here it is x sigma square cap. They have written it. We can put that as s square. Okay, the same thing here. Now the summation ui square cap, we can write it like in this format, right? Because beta 2 cap square sometimes summation xi square is nothing but your yi cap. Okay, and if you put the value of beta 2 here, then you find this value. Okay, now that part is done, so we can write like this. And the standard error, so this is only if you take the under root of the variance, then it becomes the standard error. Okay, so standard deviation and standard error both are different things. Okay, in regression we get the value of standard errors, not the standard deviation. Okay, now so homoscedasticity examples, let's go for some examples. Okay, so let's understand we are having the data on heights of students in the classroom. Okay, collecting data on the heights, okay, of students in a classroom. We are interested in how much each student's height deviates from the average height of the class. Okay, let's suppose average height of the class is x bar. If the variance of the height deviations, okay, that means xi minus x bar whole square summation and n minus 1. If this is same for all students, it means that regardless of the specific student you are looking at, the amount by which their height differs from the average is consistently spread out. Okay, that means there is a similar amount of variation in height across all students. That is, there is equal variance in height for all students. Similarly, you want to check the test score deviation. Okay, in two different sections or classes, and a standardized test we want to see how each student's score deviates from the average score in their respective class. So for group A, for group B or class A, class B, you have data for different students and find out the variance for each group. Okay. Now if the variance of the score deviations is the same for class A and class B, it means that the spread of score deviations, so the class average is consistent across both classes. Okay, so there is similar level of variability around their average score. Okay, so that is also homoscedasticity. Now, stock price volatility. So, in the stock price volatility, we want to see how the prices of stocks fluctuates. Okay, from the average price. Now, if the variance of the price deviations, if the variance of the price deviation, that means the price of the stock is deviating from the mean, how much it is deviating from the mean. If it is the same for both stocks, then there is equal level of variance. Okay, and the price volatility is consistent both stocks. Okay, so these are the examples of homoscedasticity. Okay, now let's look at the diagrams. Now if you see in this figure, okay, the first figure, in the first figure we can see that for each value of x, okay, the spread around the mean, this is our regression line. If you do this in this is like a 3D diagram. If you do that in 2D diagram, it will become like this. This is the value of xi, x1 value. Next one is x2 value. Okay, so these are the mean here. These intersection points are the mean here. Okay, and the spread is around this one. Okay, spread is around this one. So they are telling that the spread around this mean for x1 value of x is equal. Okay, for x1 and x2 they are having the same variance. That is what they are showing. So this is what homoscedasticity is about. Now if you have the variance is different, the spread of the data for each observation is different, like this figure. Okay, then we are violating the assumption of homoscedasticity, and we are entering into a different field, that is heteroscedasticity in the data. In the next video we'll talk about heteroscedasticity in detail. So that's it for today. I'll see you for in the next video. Thank you.